In this video, we are going to do an analysis of vertical circle, focusing on what are the velocities at different point on a vertical circle. Now, a vertical circle is a case of non-uniform circular motion. Non-uniform means the magnitude of linear velocity v is not the same for different points on the circle because of acceleration due to gravity. Since the circle is vertical, different points on the circle are at different height from the ground, and hence the magnitude of linear velocity v changes as you move from one point to another. So here we are going to discuss what are the values of linear speed v at different point in motion. I'm going to select 4 points on the circle, one point on the top of the circle, where the linear speed is going like this if my motion is counterclockwise. We will call this v top. Then one at the bottom, where your linear speed is in this direction, we will call this v bottom. Or to make it easier for us to remember, v top I will call as vt, v bottom as vb. And then we take these 2 points over here. I will call this v1 and this will be v2. We will find what are the magnitudes of these velocities. So let's start with the velocities on the top of the vertical circle. Imagine you are in a roller coaster in a carnival that forms a vertical loop like this. And on the top of the roller coaster, the forces acting on you is first the force due to gravity Fg and the normal force N exerted by the seat of the roller coaster on you. Now these two forces are pointing towards the center of the circle. And we have discussed before, any force pointing towards the center contributes to the centripetal force required to keep the object in circular path. So I can write the normal force plus the force due to gravity is giving me the required centripetal force Fc. Now in a vertical loop, on the top of the vertical loop, the passengers generally feel weightless. And if the passenger needs to feel weightless, the normal force acting on the passenger must be 0. So if my normal force becomes 0, I get the force due to gravity to be equivalent to Fc. Now force due to gravity Fg is given as m times g. And centripetal force I can write as m times centripetal acceleration. Since I'm finding the linear speed v, I will rewrite this expression for AC as mv squared over r. So let's substitute them here. Fg I will write as m times g. Fc I will write as mv squared over r, where r is the radius of the circular path. Now we can cancel off the m over here and rewrite for v as g equals v squared over r. Rearrange the term. I will multiply by r on both sides. So we get v squared equals r times g. Take the square root to find v. V will be equal to square root rg. Or we can also write as v on the top, vt equals square root g times r. So this is the magnitude of linear velocity v on the top of the vertical circle. Now we are going to do an analysis to find the velocity of the object at the bottom of the circle. To find velocity of the object at the bottom of the circle, I'm going to use the law of conservation of energy. Law of conservation of energy says that energy at any 2 point. So if I say, let's take the point at the top and the point at the bottom, total mechanical energy at any 2 point has to be equal. So total energy at top must be equal to total energy at the bottom. So let us write that here. Energy at top equals energy at bottom. We know total mechanical energy is the sum of kinetic plus potential energy. So I will write kinetic energy at the top plus potential energy at the top is equal to kinetic energy at the bottom plus potential energy at the bottom. Now, if this vertical circle is of radius r, I can write for its height as This distance is r and this distance is also r. So the diameter of the vertical circle, which is its total height, will be equivalent to 2r. Kinetic energy at the top will be half mv at the top squared, and potential energy at the top can be written as m times g h, which will be equal to kinetic energy at the bottom. I will write half mv bottom squared. Potential energy at the bottom will be zero because here the object is not raised at any height. Then we cancel off the m here, which is common in all the terms, and rewrite our expression as vt squared by 2 plus g times h equals vb squared by 2. I'm going to multiply by 2 on both sides because I need to find what is the velocity at the bottom and I need to keep this term here alone. So multiply by 2 on both sides and rewrite for vb. I get vb squared equals vt squared plus 2gh. When I multiply by 2, this 2 here gets cancelled and this becomes 2gh. And the 2 with vb is also removed. Now we will substitute the values for velocity at the top and the height h. We write vb squared equals velocity on the top we calculated in the previous part, that is equal to square root gr. So we write square root g times r squared plus 2g. The height on the top is 2 times r because that's the diameter of the vertical circle. So I write the height h as 2 times r. Now solve. Vb square equals, when you take square of the square root here, it can be removed. I write g times r plus 2 times 2 is 4, which is equal to 5gr. And when you take the square root to find velocity at the bottom, you get that to be equal to square root 5gr. This is the velocity of the object at the bottom of the vertical circle. Next, we use the same analysis to find velocity v1 and v2. Now v1 is at a height of r from the bottom. So height of v1 I will write as h1, which is r. I need to find what is the speed of the object at this point over here. So we do the same thing. I select any 2 points in motion and equate total energy at those 2 points. So for now, I'm going to select point 1 for v1 and the bottom of the circle. So we will write total energy at 1 is equal to total energy at the bottom. Total energy at 1 again will be sum of kinetic energy plus potential energy. And at the bottom again the same thing, kinetic energy plus potential energy. Kinetic energy at 1 we can write as half mv squared 1 and its potential energy will be mgh1. Kinetic energy at the bottom, on the other hand, will be half mvb squared, which is velocity at the bottom, plus potential energy at the bottom. Again, since the height here is 0, potential energy will be 0. Now we cancel off the values of m on both sides and rewrite our expression. We get v1 squared by 2 plus gh1 equals vb squared by 2. Then we can substitute the values of the velocity at the bottom and the height h1. In the previous part, we already found velocity at the bottom to be equal to square root 5gr. We will substitute that here. So write v1 squared by 2 plus g. h1 is the height of point 1, which is a distance r. So g times r equals vb is square root 5gr squared by 2. Solving this, we get v1 squared by 2 plus g times r equals, when you take square of the square root, you can remove the square root sign and write this as 5gr by 2. Next, I will multiply with 2 on both sides to get rid of the 2 with v1 squared. So when you multiply with 2 on both sides, you get v1 squared plus multiply 2 with gr equals 5gr. Now move 2gr to the other side, you get v1 squared equals 5 gr minus 2 gr. That gives you 3 gr. This is V1 squared. So if you want to find V1, you take square root on both sides, and that gives you V1 to be equal to 3 gr. So this is the velocity at point 1. At point 2, you will get the same magnitude of velocity because both of these points are at the same height. So in a vertical circle, if 2 points are at the same height, they should have the same magnitude of velocity. So if my V1 is square root 3 gr, V2 also has to be the same value if they are at the same height. So to summarize, for a vertical circle, the velocity on the top of the vertical circle is given as square root gr. The velocity at the bottom of the vertical circle is given as square root 5 gr. And the velocity at a point midway on the vertical circle can be given as square root 3 gr. So these are the three important velocities you must remember to solve problems related to vertical circle. So let's apply what we learned in a problem. We take problem 9.15. In solve problem 9.1, with what speed does the roller coaster car have to enter the bottom of the loop in order to produce the feeling of weightlessness at the top? So if you want to feel weightless at the top, you need to find at what speed should you enter the bottom of the loop. And we already discussed in the previous part that velocity at the bottom for the vertical circle is equal to square root 5 gr. And while deriving this value of velocity, we already considered that on the top you feel weightless. So I can just substitute the values of g and r. In solve problem 9.1, the radius r was 5 meter. I will use that to solve this question. To get square root 5, g is 9.81 times 5. And when you solve this, you get the velocity at the bottom to be equal to 15.66 meter per second, which you can approximate to 15.7 meter per second. So my correct answer will be option D. So if you remember the values of these velocities, it's very easy to solve problems on vertical circle. Next, let's discuss a case of rotating cylinder. So in question 9.11, a figure shows a rider stuck to the wall in the barrel of fun at a carnival. Which diagram correctly shows the forces acting on the rider? So a barrel of fun is a cylindrical ride where it rotates with a specific angular velocity such that the rider is stuck to the wall of the barrel without falling. So if you have a cylindrical barrel like this, and there is a rider stuck on the wall, the forces acting on the rider will be first the force due to gravity, which is acting vertically down. We call it Fg. And since the rider has been pushed towards the wall of the wall of the cylinder will exert a normal force acting perpendicular to the surface. So I have my normal force here. Now the rider is stuck on the wall. But you have the force due to gravity acting downward, which can try to pull the rider down. Which force will prevent the rider from falling? So since the rider is stuck on the wall, it is the friction between the rider and the wall that prevents the rider from falling down. So next I have the force of friction, which acts opposite to the force due to gravity. So when you look at the diagram of the force, it looks like this. You have a force going down, up, and the one going, which is option A in your answer. So the correct answer to question 9.11 will be option A.